Hey everyone, I'm Prajit from Basira Lab at Imperial College London. Today I'm going to talk about FireGNN, Neuro-Symbolic GNN with Trainable fuzzy rules. This part of the research is on explainable graph neural networks, particularly on medical AI datasets where trust and interpretability are crucial. Before diving into this research, let's understand what do I mean by the medical AI dilemma. So there's Dr. Sarah who asks the system, hey, is this image of tumor malignant or not? And the system says, yeah, it's malignant and it's 95% accurate. And then, obviously, as a doctor, she's inquisitive and she asks, why? What's the reason? And why have you predicted 95%? And the AI remains silent. Obviously, most of the neural networks architectures like CNN or any other biological neural networks which we have right now in this modern world all can show numbers, weights, attention weights, and all different sort of parameters. But none can give you any sort of set statements or rules or any understanding of show them that why it has predicted in that manner. And that's a big problem because this leads to three things. One, black box decisions. And obviously when there's black box decisions, that moves to there's no clinical trust. And also there's no readable rules or why did this prediction happen or what did this follow while making this prediction. Did it follow any sort of rules or did it follow any sort of statements or any logic or what was the reasoning behind it? So how do we solve this? Before diving into solving this through our method of FireGNN, we also need to understand some concepts like what's Neuro-Symbolic AI is. So it's nothing more. It's very simple. So Neuro-Symbolic AI consists of two things. One, a symbolic reasoning, and second, neural networks. So when we combine symbolic reasoning and neural networks, it brings sort of a logical reasoning in the neural network architecture. So it bridges both the neural networks as well as the logical reasoning. So it's faster to reason about with the logic in a neural network. Let's see some of the examples of what do I mean by Neuro-Symbolic AI. So if you see logic rules, visual, relational, RL constant, probability fact, there's such examples like if cat X then is mammal X. And there and or operators, different type of parameters, which we find in Neuro-Symbolic AI, and we'll be focusing on some of them here. Now, let's also understand another concept, a very interesting one: fuzzy rules. So, what is it? What are fuzzy rules? We know what a rule is, right? A rule is something in which something is there, a statement is there, and it happens yes or no. But fuzzy rules are not like that. So they are not black and white rules and not like true or false. They are more of a degree of truthness and degree of how false it is. So for example, if degree more than equal to theta 1, then high connectivity. So if you can see theta 1, when it's more than equal to 10, it's showing theta is 0.5 through. And when theta 1 is more than equal to 15, then the theta of the degrees of truth is 0.6 true. So second statement has higher truthness value to it. So this in fuzzy rules, it's not that one rule is wrong or one rule is right. It's how that rule pertains or is truthful or it's more impactful in this particular data set or in this particular situation which we are speaking the rule of right now. So this is a more fuzzy rule. So fuzzy rule is just doesn't turn on off, it activates with a certain strength. Now, coming to the problem which we have with this fuzzy rules is that when we have a rule and it's crafted, so this degree more than equal to 10 is high connectivity. This can be pertaining and is right for organ CMNS dataset, but for other dataset like blood eminence, tissue eminence, morpho eminence, the degree is different. For example, for blood eminence, the degree is more than equal to 16. Then that rule pertains to it, or then the rule is applicable to it. If for tissue eminence degree is more than equal to 26, then the rule is applicable to it. So how do we make such a rule which is applicable to all of them, or do we do something else, or is it some other thing? And that's where we come with FireGNN, where we bridge Neuro-Symbolic AI, which we just learned, fuzzy rules, which we just learned, and something also on how to train these rules. So it's a combination of Neuro-Symbolic AI, fuzzy rules, and training the rules of it. So let's go step by step within each of this architecture. So first step is building the graph and getting the features of it. So if we have a medical image dataset, we take each image from it, and each image is vectorized into a node. So for example, node 1 might be liver, node 3 might be kidney, or something like that. And so each node, each image, a PNG or a JPG is vectorized into F1, F5, F3, F5, something like that, and forms a node. Now, all of these nodes are connected through cosine similarity, which forms the edges. So it's like top k. So top 2 or top 3 edges within each of these nodes are connected together, and thus it forms a graph. Bingo, we have a graph now. Once we have a graph, we can extract what? Features. And these features are like, for example, node degree. So like how many nodes are connected to this particular red node, for example, here. It's like 4. Next, we have a feature which we extract is the clustering coefficient. How many neighbors of the node which is connected are neighbors to each other also, are connected to each other. So they are 2 here. And last but not least is the 2-hop label agreement. So what is the label of the second hop of the neighbor pertaining to our current node in which we are standing? So these 3 features we extract from each of the graph of a particular data set. And after we extract this, we take these values and then form the rules. So let's come to rules a bit. To build these explanations, we form the 3 fundamental rules from those 3 features which we just extracted. Before going to and seeing the rules, how it's formatted, how it's formed, we need to understand that each rule has 2 things. First, if degree is high connectivity, then this, and this particular rule is parameterized by 2 things: decision boundary, which is theta, and rule activation sharpness. So decision boundary is something in which at what value is this rule can get activated, and alpha is how sharpness is the activation to be. So for example, if it's a high alpha, then it gets activated with even if it's a slight change in the theta. So it might be like a 0.3 or 0.6 and it will change, and the rule gets activated and fired automatically. So the 3 rules which we are talking about. So first rule is high connectivity, second rule is of clustering, which is of high clickiness, and third rule is of label agreement, which is high level consistency. These are the same 3 exact features which we extracted from each graph, and that's why we can form these 3 rules. Obviously we can form other rules later in future, but this is just for a research paper to show you, explaining how these things are working. But the problem now, we formed the rules, we formed the rules from each of the graph, we extracted the features, that's good. But these rules are fixed, right? From each graph, we know theta 1, theta 2, and theta 3. How do we make them not fixed or something like that? So what if we make them trainable? And that's what FireGNN is about. Trying to make these rules trainable so that they are applicable to each of the data set. Let's see a glimpse of it. What do I mean by if rules are trainable? So here you can see a GNN, and in GNN I started the message passing, which epoch, if you can see epoch 9, 10, 11, each epoch is rising. The values of each rule, for example, in rule 1, theta 1 and alpha 1 is changing. Same for the other rules, same as follows, like rule 2, rule 3. And this epoch goes to, for example, epoch 49, when the message passing stops. And you can see all of these theta 1, alpha 1, theta 2, alpha 2, theta 3, alpha 3 have all converged and stopped now. And they've converged to a particular value, like for example, theta 1 is 7.28, alpha 1 is 5. For that particular rule and for that particular data set, like here it's organ C MNIST. So for organ C MNIST, rule 1 has this degree for 7.28 at this when the message passing was happening, and alpha 5. So if the theta increases from this, then this rule 1 gets activated. Same for rule 2, same for rule 3. So for each of these rules, for each data set, which is organ C MNIST, we have the values for all of them. So this way, we make the rules trainable. Now, we have to understand the learning pattern and logic behind this training. How do we got this vector? So we have the fact vector, which is the degree, clustering coefficient, and 2-hop label agreement. And we also, if you remember, we have the alpha and theta values from earlier when the rule is trained. So once we have this alpha and theta values, we have the rule activation sharpness and decision boundary, and this together puts into this formula and forms the activation of rule I. So for instance, if R1, this rule 1, is equal to 1, it suggests that node has a higher degree. Because if you remember, R1 is node for degree, node degree, R2 is for clustering coefficient, R3 is for 2-hop label agreement. And this R1, it always ranges between 0 to 1. And so if it's closer to 1, then means it has a higher degree and it has to have a higher value to cross it. Now, if you interestingly notice, there's something known as firing strength vector RU. So it is a combination of this node degree, R1U, clustering coefficient R2, and 2-hop label agreement R3. When these 3 are combined, it forms a firing strength vector, which is RU. And once this RU is crossed, then it shows that these 3 rules have passed in the particular data set. So let's also see the analysis of theta 1. For example, theta 1 is the degree, the node degree. for different data sets. So how for different data sets the theta 1 is changing during message passing, how it's getting trained. So if you see in morphoemnus, it's increasing quite high, while for bloodemnus or organ seam, it's decreasing, which makes sense because morphoemnus has quite a high amount of nodes, and it's quite a big data set. Once it's big data set, obviously a high amount of nodes, and the degree of each of the nodes are also quite high, and that's why the node degree is 11.52 when it has converged. So to get the final prediction, we inherently combine all these learned embeddings with these fuzzy rules. So where do we get the embeddings from? So normally during a GNN message passing, always there is something known as H, which is the embedding, and each node gets an embedding which is updated. So if you can see, each node has a HU which comes into place from the message passing which has occurred, and then also from the below, if you can see, we have the R, which is the R vector, which is the R1 plus R2 plus R3, which we showed you earlier. We combine these two, and then we form H dash, which is the new updated embedding of the GNN. And then it goes into classifier to classified. So this gating mechanism knows which to influence more or which is more. For example, if HU is more important or R is more important. So that way the gating is done. So for example, if we go more in deep how the gating mechanism works is we project the rule vector in the GNN embedding space. So if you see the RU is rule vector where we have WR and BR, the weights and biases, and we form the EU. Then we concatenate this EU with the HU, and then we compute the gate vector GU. And this GU has the dot product with the HU, and we can see this forms the H dash U. So intuitively, if you notice, if the rule-based information is highly relevant, then if the GU increases the influence of EU, and otherwise, obviously, it favors the original embedding HV. So if the rules are important, then the value of the GU gets increased, and obviously, it focuses more into the rules value. But if it's not so important, for example, if 1 out of the 3 rules get activated, it's not so important, then obviously the original embedding gets more influenced. So explainability. So when we get this training, when we got these rules, we also understood how the rules are computed, how the new embeddings are formed. But okay, this way we are improving the performance. What about explainability, which we talked about? So when we look at the calculated firing trends, which we have the R1, R2, R3 for each of the data sets, so we know now that if R1 was high, like example 0.6, and R3 was also high with 0.56, we can generate a human readable explanation that way. We can say that node was classified as splin because of high connectivity and high level consistency. Because the rules of these two, R1 and R3, were activated while R2 wasn't activated because it wasn't so high. So this part forms an interesting part of the model, and this way we can have a good explainability even while improving the performance. So we benchmarked against some auxiliary tasks. We also took some different tasks, like we upgraded embedding through homophily prediction and similarity entropy prediction. But even after we benchmarked, we saw a very modest and incremental improvements, while for FireGNN, the improvements were quite high. So before going into the results, let's understand the computational efficiency of the models. If you see a normal GCN, its time takes is like 0.48, while if you add an auxiliary, obviously it increases from 1.9. If you add fuzzy rules, it increases more, 3.12, which makes sense. So in most of the cases, if you see, the fuzzy rules have taken a higher time, but a lower memory. So if you notice, GCN, for example, it started with 758 for organ CMNS dataset. It started with 758.95. For increase to 944.24, but for FR, which is the fuzzy rules, it came down to 519.28. The interesting fact is that the fuzzy rule model is quite memory efficient, because when we're using FR, when we're using fuzzy rules, it knows at which rule it has to focus with, or when it's updating the embeddings. So it doesn't have to look from this side to that side to these different sort of parameters, different sort of topological features. I know the particular which rule is activated, which has higher influence, the H has higher influence, or the rules have higher influence according to the gating mechanism. And this way the computation memory decreases, but obviously the time increases because we have to compute a lot of things. So adding the fuzzy rules increases time due to extra logic and computation, but the memory, it's more memory efficient. So coming to the performance, if you notice across all the datasets, organ C MNIST, organ MNIST, S MNIST, tissue MNIST, learn MNIST, and morpho MNIST, there's 3 to 4% increase across all datasets when we are using the GAT plus fuzzy rules, or GCN plus fuzzy rules, or GIN plus fuzzy rules. Also on large datasets like tissue MNIST and morpho MNIST, when we are using with GAT, the fuzzy rules, it's getting out of memory, obviously, because attention mechanism does take a lot of calculation and memory consumptions. Sensitivity also increases 3 to 5% across all datasets, which is quite crucial in medical datasets. And the F1 score increases from across around 2 to 3%. So in conclusion, the strength of this model is that it's very data adaptive reasoning. So it learns the fuzzy threshold and sharpness directly from the graph structure. So for each of the different data sets, we don't need to worry about, okay, this is a known data set, now what about the rules? We can easily find different threshold rules for that data set once we train in that particular data set. For example, if we have 5 data sets, we can have 5 different rules, same node degree rules for each of the data set. Also, it's topology aware learning, which is a very important thing, because in graphs we have a lot of topological features like degree clustering, level consistency, eigenvector, and many other between centrality and many other such topological features. So we can learn a lot from graphs, so we are leveraging that here. And the certain research direction is like we can expand this rule vocabulary. Here I have just shown 3. We can expand it to more 5, 6 rules. And also, interestingly, we can also have a dynamic graph extension where we can apply FireGNN to some evolving biomedical network, where the graph evolves time to time, like the graph changes, like there are more nodes, more edges, and then we see how the rules changes in the same data set. That's it. Thank you so much. Have a good day.